Okay, so let's start having a look at some of these hydrocarbon families that we need to know. Okay, so essentially all hydrocarbons are grouped into two main groups, those being saturated hydrocarbons and unsaturated hydrocarbons. You may have heard these terms before in talking about fats and oils, okay, and that's because unsaturated hydrocarbons form your polyunsaturated or unsaturated fats, which are your oils, and saturated hydrocarbons, one of those can actually be looking at your saturated fats. Okay, so the key thing for you to understand here is that saturated hydrocarbons contain only carbon-carbon single bonds. So every bond between carbon atoms, okay, like these ones here, okay, or this one here, every bond between a carbon atom in a chain is a single bond. Whereas in unsaturated hydrocarbons, we've replaced one of those single bonds with a double bond. And you'll notice here what that does is actually reduces the number of hydrogens by 2. We've lost 2 hydrogens in order to form the double bond. So in a saturated hydrocarbon, it has the maximum number of hydrogen atoms, whereas in an unsaturated hydrocarbon it can have one or more double or triple bonds in it, which makes it an unsaturated one. Okay, so when we talk about these families of hydrocarbon series, we have a special name for them and we refer to them as a homologous series. When it comes to hydrocarbon molecules, we talk about a homologous series. So in a homologous series, okay, we've got a group of organic compounds, so hydrocarbons, that contain the same functional group, and we'll talk about functional groups again later on after the holidays, and they have the same general formula. The key thing to remember in this definition is that they differ only by a CH2 group from each successive member. So one way to think about this is if I look at CH4, the next one in the series for methane is C2H6, okay, and you can see here that we've added a CH2. We've gone up by 1 carbon and 2 hydrogens from one member to the next. Okay, so that's what we mean by having an additional CH2 group. Because they have all the same type of bonding, these are all single bonds to carbon, or if they've got that double bond, they have the same functional group, so they tend to have very similar chemical properties. Okay, remembering that chemical properties are the way they react with other things. And then we see a general progression in their physical properties. So if we look at this graph here, we can see as the number of hydrogen carbons, the carbon atoms in our hydrocarbon increases, we see a steady increase in the temperature of the boiling point. And we can see that in this graph here too, looking at methane, ethane, propane, butane, pentane, and hexane. These are all part of the alkanes homologous series, and we can see that from one member to the next, we see a steady increase in its melting point, boiling point, and then it steadily moves from gases through to liquids. Noting here that at carbon 4 is the last gas that we have. So in a homologous series, they'll have similar chemical properties, and we'll see a steady trend in the physical properties from one member to the next. Okay, so the first homologous series that we're going to look at is the alkanes. These are the simplest of the hydrocarbons. They have only carbon and hydrogen, and every bond is a single bond throughout the molecule. They have this general formula here, CnH2n plus 2. So this means that for any number of carbon atoms n, it will have hydrogen atoms equal to 2 times n plus 2. Please note that this is not meaning mole. This is just like X. You could even call this X, CXH2X plus 2. Same thing. Okay, it's just an unknown. So let's have a look. Molecular formula is our CH4. Okay, so 1 carbon to 4 hydrogens in every methane molecule. Its name is methane, and the semi-structural formula is where we start to put them together in groups that they are bonded in. Okay, so in this case it'll be CH4. For ethane, we're going to go up by 1 CH2 group. So in this case, we're going to follow our formula, CN, so C2 H2N plus 2, so that would be 4 plus 2 is going to be 6, so C2H6, and then my semi-structural formula is actually going to be CH3CH3. Okay, because we're going to have a carbon bonded to 3 hydrogens that bonds to another carbon bonded to 3 hydrogens. Okay, let's have a look at propane. Propane is going to have C3, okay, and then H2N plus 2 is going to be C6 plus 2 is going to be 8, so C3H8. Okay, our semi-structural formula now, CH3, and we said that we're going to go up by a CH2 each time. So I have a CH3 on each end of my hydrocarbon, and now I've got a CH2 in the middle and another CH3 on the end. So I've got 1, 2, 3 carbons and my 8 hydrogens. Let's have a look at butane. Okay, C4, H2N plus 2 is H10. I'm now going to have CH3. I'm going to insert another CH2 group. So I've got CH3, CH2, CH2, CH3. Okay, hopefully you can see the trend that is appearing here, and I want you to have a go at filling in the rest of the table. You can do that one, and I'll do decane down the end here. So hopefully if you realize that this is 1 carbon, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so decane is going to be C10, H2N plus 2 is H22. So CH3, 2, 3, whoops, counting the wrong thing, 3, 4, 5, 6, 7, 8, can I fit it in? 9, and another CH3, 10. Normally you wouldn't put that one off the end, but you'd put it at the end there, and I've run out of space. The other way to write this is CH3 bracket 8 lots of CH2 and then another CH3. Okay, so this is our condensed formula. So we do this when they start to get too long. So I want you to fill in the rest of that table, and then we'll look at how we look at our structural formulas. Okay, so structural formulas, you need to know how to be able to draw up to and name alkanes up to C10, all the way up to decane. Okay, so let's have a look. We know how to draw methane, hopefully. Remember, it has a tetrahedral shape around the central carbon. Now ethane, I'm going to have my 2 carbons. Remembering carbon with 4 bonding pairs is going to have a tetrahedral shape around each one. If you are in class, you can grab one of the Molly-Mod kits and build these as you go. They'll help you to draw the structural formulas. So I recommend that while you're working through this, grab one of your bonding kits and have a bit of a play around and build some of these structures as we go. Okay, propane, we've got 3 now. Now it's important, in order for us to maintain our tetrahedral arrangement, that we draw our backbone in this zigzag. So now I'm going to put my 3 hydrogens on here. Oops. I'm going to put my 2 here, and I'm going to have 3 more off here, ensuring every time I do this that I have 4 bonds around my carbon atom. Okay, hopefully you can figure out where this is going. I'll draw in pentane for you here. 1, 2, 3, 4, 5. Notice I'm forming that zigzag pattern, and then I go back in and fill in all my hydrogens. And there we have pentane. So have a go, and in your books I want you to do butane, and I want you to do hexane as well, so that you've got them there. And this is our ball and stick models, showing what they are. You'll notice that these ones are often drawn flat in textbooks and things. Please do not draw flat on tests or exams. Okay, you need to show the zigzag form to show that you understand that it's tetrahedral, not 90 degrees around your carbon. Okay, so as the chain size increases, number of atoms increases, which increases our chance of instantaneous dipoles. Hopefully you remember that from covalent bonding. So therefore, these are all non-polar molecules, the alkanes, and as they get larger, the strength of our dispersion forces gets larger, so our boiling point increases. Okay, so this is just a bit of a note on empirical, molecular, and structural formula. Hopefully you remember that empirical formula is the lowest whole number ratio of elements in the molecule, and the molecular formula forms the actual number of elements present in the molecule. The molecular formula for each of our hydrocarbons and the families that we will look at are given by these general formulas here. Okay, alkanes is the one that we've just looked at, CnH2n plus 2. Alkenes is CnH2n, and alkynes is CnH2n minus 2. Okay, the other thing to remember is that we always have different ways of representing molecules. You will see them represented in a number of different ways in your papers and in your textbooks, but in your exams you are expected to do particular forms. So for your structural diagrams, if it asks you to draw a structural diagram, you should always remember to show all bonds. You can't leave off any hydrogens or anything like that. You'll lose marks. And you need to show the zigzag conformation. Okay, so the structural diagram shows all atoms and bonds in the structure. You should not draw these, okay, or draw them flat, just remembering to keep the zigzag, but you should be able to understand them when they're shown to you. Condensed structural formula is also known as our semi-structural formula, and that's this one here, where we show the sequence of how they're joined together in a chain and the way that the atoms are actually grouped. Okay, so it gives us an idea of how the molecule is formed, but without us having to show all the bonds. Okay, and then skeletal diagrams is this guy here. You may see them on test papers, but you are to not use them. Don't use them when answering questions. Okay, wait till you get to uni and they'll let you use them then, but not when we're answering questions for VCAR. Okay. Just a bit of review. I know this video is going a bit long, so I want to wrap it up, but a bit of a review on combustion reactions. Okay, you should have a practice at balancing these. All our hydrocarbons will undergo combustion reactions, which means that they'll react with oxygen to form carbon dioxide and water for complete combustion, giving off heat and light. Okay, these are the rules for balancing combustion equations. Okay, so have a quick go through them. Identify the reactant and products. Okay, so which ones are which. Write the chemical formula for all the reactants and products. So if it's complete combustion, we know that will always be CO2 and H2O. Balance the carbons first, because as you can see here, the carbon only ends up in one place, which is CO2. So it's always better to balance the carbon first. Then you balance the water, okay, the number of hydrogen atoms by the water, and always balance oxygen last, okay, and then put all your states in. Remember, for incomplete combustion, we'll get black smoke and we will get a mixture of carbon dioxide and carbon monoxide. You won't be asked to balance incomplete combustion reactions unless the question specifies the ratio of carbon dioxide and carbon monoxide. Okay, but you are expected to realize when it says complete combustion, okay, that we go all the way through to CO2 and H2O. Okay, so that is our first homologous series, alkanes, and we'll go through the next one, alkenes, in the next video.